Okay. Hello, everyone. I'm very glad to be here. Thank you to everyone for the amazing talks. I'm really enjoying them. My name is Aman Jagwani. I'm a PhD student at Maynooth University. I'm working with Professor Victor Lazzarini over there, and my focus is on FPGAs and creating a self-accompanying cross-adaptive synthesis system, a standalone synthesis system. So we're trying to do that on FPGAs. So today I'm going to talk about modular sound synthesis on FPGAs with the high-level synthesis development flow. Just a quick note is that synthesis and high-level synthesis, or HLS, is not sound synthesis. It's more about actually creating hardware from code. So if I refer to HLS, that is different from the actual sound synthesis. Little bit background about me. I'm an audio programmer, sound designer. I also have a background in electronic music and jazz drum set as well. And then right now I'm a researcher in the field, in more the embedded system kind of field. Yeah. So before we start, I'm just going to give an overview or like an introduction of FPGAs. FPGAs, or field programmable gate arrays, are integrated circuits. They're like chips. They're like the microcontrollers or CPUs or chips that are on our phones and all our devices. The difference is that they are reprogrammable and customizable. You are actually able to change the electronic circuits, the logic units that are within the chip. It's mostly done with specialized hardware description languages like VHDL and Verilog. What I'm focusing on today is another technology called HLS, which enables us to program FPGAs from C or C++ code, basically. It's very specific, and it's still not, it's called high level, but it's not actually that high level. It's still quite low level. But there is if you have a good approach and a systematic approach to it, it is possible, and it is accessible, I feel, to the audio developer community. So one of the goals of my talk is also, and the project that I'm working on is also about bringing more access and uses of FPGA in the research and industry as well. Another factor about FPGA is that it has a high degree of parallelism. We are able to customize the actual processor that we make, or like the code that we make. So we are able to do a lot of functions and a lot of things in parallel on the FPGAs. That is very useful for music and audio. For example, in spatial audio, we can have many parallel processing channels happening together. Then there's also ultra low latency. In FPGAs, you don't need to work with buffers. You can do a lot of very heavy processing sample by sample. So that results in ultra low latency in the order of magnitude of microseconds, which is really powerful for real-time audio processing. Another thing is, on FPGAs, we can work with extremely high sample rates, like high in the megahertz, like above 25 megahertz, around 100 megahertz as well. So we can actually do our audio processing at those sample rates. So that means that we can achieve very close to virtual analog. We can achieve alias-free, higher order FM synthesis, for example. Another thing that we can do on FPGAs is there's a large number of GPIOs, or general purpose inputs and outputs. So that means you can have a lot of channels again. So like doing spatial audios, huge arrays of speakers, they can all be processed parallelly without any problem on a single small chip. Some examples of FPGAs in the audio industry and in research are, the first is a synthesizer example is Novation Summit. The oscillators are like virtual analog oscillators, run at extremely high sample rates to achieve the sound. If you hear it, you'll know like it sounds really good. Even the UDO Super 6, similar thing, the oscillators are run on FPGAs. So they leverage the super high sampling rates. Then another example is Antelope audio interfaces. They have analog emulation of different kinds of effects on their interfaces, which are run on the FPGA. So that leverages the extremely high throughput and processing capabilities of FPGAs as well. And then a very prominent research project is the Cifala project by the Emeraude team in France. So they have created this toolchain called Cifala that enables the programming of FPGAs with the Faust language. Faust is a domain-specific language. It's for DSP programming mostly. If you haven't checked it out, you can create very, very powerful DSP applications, synths, effects with Faust. and it's quite accessible. And with Cefala, they translate Faust straight to flashing an FPGA. So definitely check them out on the GitHub. It's a great way to be introduced to FPGAs as well, and you can make a program pretty quick on running on an FPGA with Cefala. And they also use HLS, which I'm going to talk about soon. So they convert the Faust to HLS, and then HLS, which is C or C++, HLS gets converted to hardware code, and then that gets flashed onto the FPGA. So I'm quickly going to talk about the hardware that I'm using for my examples. There are two very prominent manufacturers of FPGAs. One is AMD Xilinx, and the other is Intel Altera. So I have worked in the Xilinx side of things. So I use this board, which you can see on the screen. It's the Digilent Zybo Z720 FPGA board. So it's a complete board with the FPGA in the middle, which is the Zinc 7000. It is actually a system on chip, which means that it's not just the FPGA on the chip. There's also some memory, BRAM memory, and there's also a dual-core ARM Cortex processor, so just a CPU. So on that single chip, there's a processing system and the programmable logic, which is the FPGA part. And one of the challenges with working with these chips is balancing what you put on the CPU, what you put on the FPGA, and how they are interconnected and how they're interfaced as well. So generally in the CPU, we do more things like control systems, like sending control signals, updating parameters for our synthesizers like frequency, modulation index, things like that. The CPU also initializes all the hardware, so the hardware peripherals and as well as the hardware that we are coded onto the FPGA. The CPU has all the drivers for all of that and enables you to configure and initialize them. And it helps with the peripheral communication as well. So peripherals are things like the audio codec. So from the chip, we have to send our digital audio to the audio codec that has the converters that basically has the DAC. So the communication with that and the configuration with that is done on the CPU as well. And it also communicates with other peripherals like sensors, ADCs. There's UART communication, which enables you to do MIDI control as well. So all of this happens on the CPU. And then on the FPGA side, that's where we do things that need low latency, things that need high processing power, and basically our main audio synthesis like computing audio, processing audio, all of that is done on the FPGA, and that audio is sent to the audio codec. The CPU configures the audio codec, the FPGA sends audio to the audio codec. And then there's also DDR memory on the, now out of the SoC, there's also DDR memory on the board, which both the CPU and the FPGA have access to. So to recap, we have like the development board, which is the Zybo Z720. And then inside that, we have the Zinc 7000 SoC. And inside that, we have the FPGA and the CPU. So yeah, so now getting into the HLS part. So like I said, traditionally, FPGAs were programmed with very specific, and are still programmed with very specific hardware description languages, which require specialized hardware knowledge that is beyond my scope as well. And it's something that is not generally in the scope of the audio developer or community. So HLS provides some mitigation of that issue to some extent. HLS basically, you have a C or C++ program that gets converted into the hardware code. So these are automated tools that are provided by the vendors. Xilinx has, Intel has as well. So within Xilinx, there are three tools. There's Vitis HLS, Vivado, and Vitis IDE, like I've shown over here. So Vitis HLS is where we do the HLS programming. That's where we do our C++ code. So that's where we design the standalone sound synthesis IP core. So IP core is a terminology, it's intellectual property. It's a terminology where each module or hardware unit you create is called an IP in the hardware world. So within Vitis HLS, we take a C or C++ program, and that gets converted into this IP core. Then we do the testing of the C program as well as the testing of the hardware generated within Vitis HLS. So after that, we move to the next software, which is Vivado. That's where we have like a block diagram. I'll show some examples soon. and where different hardware modules are connected. So we can think of like in HLS, we create different parts of a modular system, like oscillators, filters, etc. So we integrate all of those things in Vivado in like a block diagram. And then over there, it gets basically converted into a bit stream, which is flashed onto the FPGA eventually. In Vivado, we can also do debugging with things called integrated logic analyzers, where you can digitally probe your generated electronic circuit on the hardware. And then we move to Vitis IDE, where we program our CPU, which was there on the SoC as well. So that's where we make the drivers, we initialize all the hardware that we generated as well, and make sure all the configuration and initialization is done. And after that, on the CPU, you can also design your control system for assigning parameters, launching gates for envelopes, things like that. Yeah. So just quickly, this is the programming structure for HLS. It's centered around a top-level function, which is what gets converted into a module or IP core that I was talking about. The top-level function, in that we put all our DSP, we put HLS or put optimization directives, and we use very specific data types. I'm not going to get too much into the details of HLS programming. This is more about the structure and the approach and the design considerations. So our top-level function is basically analogous to what our module will be eventually on the FPGA. So for example, if it's an oscillator, all my oscillator processing will be inside the function. Then we have input arguments and output arguments, and they all have to be, again, specific data types, and interfaces have to be defined according to the ADCx standard, which is the standard used in hardware and all of our integrated circuits and embedded systems and all. Again, not going to get too much into details, but basically that's how we decide how we communicate into and out of the module. And then then we test the function within Vitis HLS with a test bench. You test the C function, but you also test the generated register transfer layer, which is basically the generated hardware within Vitis HLS. With the same test bench, you can do that. And then you basically generate the hardware and export it into Vivado. So the main aspect of what this project is, we are trying to translate a modular synthesizer on FPGAs. So modular synthesizers are basically constituted of different modules that are interconnected, and you create different sonic possibilities with them. Similarly, FPGAs are reprogrammable as well. So leveraging that aspect of it, if we have a collection of modules like as IP cores, what I spoke about, we can interconnect them and change them and create different kind of sound synthesis possibilities with just one set and one system of things. So that is the paradigm that we are working with here. The interconnectability and reprogrammability is the main aspect. So what the system consists of right now is basically an expanding collection of sound synthesis HLS IP cores. They're already generated, they're ready. So they consist of like oscillators, envelope generators, filters, mixers, everything you have in your modular synth. We are making IP cores for that. And then there's a base audio system. So in the FPGAs, it's not easy to just get audio out of it. Nothing is made, there's no libraries, there's no drivers ready. You have to do everything from scratch. So our system also takes care of that, audio input, output, drivers for the audio codec, drivers for different peripheral IP cores, and as well as inter-module communication. Everything is basically, the goal is just drop the HLS IP cores and make your synthesizer. And then we also have a control system on the CPU. So that's what I was talking about, changing the parameters and stuff like that. So there are options for that. We can have we can make a generative piece on the CPU in C or C++ that uses the IP cores to play as its instruments. That's also possible. We can have GUIs. MIDI is also, we've implemented MIDI as well, and you can use different kinds of sensors as well. So that's all done on the CPU with the control system. So I have a couple examples to show you. The first one is subtractive and additive synthesis, like a combination of both, because we have an oscillator bank with 4 outputs. It goes through a virtual analog Moog emulation filter. And yeah, these are basically the IP blocks that we have in that we are using with them. And we also, this design also shows the Zing processing system, which is basically the CPU that has all the control signals. That is controlling all of the different IP cores. And then that's sent to the I2 transmitter, which just basically does data conversion for the audio codec to understand. So here's a quick demo of that. Sorry. I think it's not sharing the sound. The sound is playing from the computer. Sorry about that. Yeah, so that's just an example of subtractive and additive synthesis happening together. Then we also have dual operator FM synthesis. Quickly gonna go over this in the interest of time. Yeah, so that's basically the same same system, two completely different synthesizers. You can switch quite easily between them. Some applications of the system would be quickly prototyping different complete hardware synthesis implementation all on one chip. Yeah, and just deploying them quickly, easily, like for companies, for commercial applications, you can quickly make different kinds of synthesis. It's very powerful. It's everything on one chip. It's not just like a filter on one chip. It's a whole system on one chip. Yeah, and then eventually we are working on making this even higher level, and an application would be to make like a Mac-style graphical interface for generating hardware designs of modular synthesis. Works in progress right now are additional IP cores like reverbs, delays, spectral processing, more control surfaces as well. And we're also working on C-sound acceleration. So C-sound is a sound and music computing system like Pure Data Super Collider. We have C-Sound running on the board already. We made a bare metal build for C-Sound and it's working on the board. Now we are working on interfacing them with the existing IP cores and making new IP cores for the unit generators and opcodes of C-Sound. So yeah, that's it. Thank you. Hope you enjoyed. Questions?
Yeah. So within the FPGA itself, you have the actual FPGA with the gates, and you also have the CPU and peripherals. So wouldn't there be a bottleneck, like, because the audio is eventually going through the peripherals and the DAC and so on? So that will have the constraints, like digital constraints. So won't that be a bottleneck in speed and performance, even if you're using the FPGA?
Yes, definitely. That's a great question. So yeah, right now I'm just using whatever's on the Zybo board. So we are limited by the audio codec on that board. So even though I can run everything at extremely high sample rates, I'm still doing normal 48K. But there's an ongoing project with the Sifala team as well and with our university as well for higher order FM synthesis particularly, which uses ultra high sample rates, for example. And for that, we are developing like very fixed, like specific hardware to go over the bottlenecks. Like the French team has already developed a DAC for that, so that it works with higher sampling rates. We are also looking at HLS implementations of DAC for high sampling rates. Yeah, but that's a great observation.
Can you elaborate on some applications that can be accomplished using an FPGA but cannot be accomplished with a bare metal high-end processors like RISC-V or Raspberry Pi?
Yeah, definitely. So firstly, the very high sampling rates, that's not always possible on something like a Raspberry Pi. Then the parallel aspect of it, outputting large arrays of speakers and doing spatial audio in real time also. On FPGAs with the amount of GPIOs, you can do a lot, and also with the parallelization, you can do a lot. Then another thing is the ultra low latency. The FPGA latencies, like once we get over the latency induced by things like the audio codec, the possibilities of latency on FPGA is extremely low. So things like active control of acoustics, that's again something being worked by the Cifala team. And also just signal processing at extremely low latency is also something.
Aman, can you build a codec in FPGA that like instead of depending on the I2S bus to decode it, because it's field programmable logic gates, can you just convert that to send it out? Is that possible?
Yeah, it is. So that's also something work in progress. Just bypassing the whole audio codec and communicating out of the FPGA for the audio. You can definitely build it. There has been progress. People have built it with VHDL and like normal FPGA programming. We are also trying to do it with HLS itself, and then you just output audio directly from the FPGA pins. So that will be a major. That will be very helpful in realizing the actual benefits of the especially low latency.
Hi, here. Can you also tell me how we can, in HLS maybe, how can we build maybe IP cores that allow us to use like AI models, like for the same sort of reverb, these kind of audio effects?
Yeah, I mean, you can definitely try, but there will be constraints on this as well, like the amount of logic units available. But it's basically HLS programming is very specific C++ programming, so it's not as simple as like just taking an existing model. It will have to be a lot of redesign or even just doing it from scratch. But for example, the thing we did with the filter, that's a existing Moog 4-pole filter emulation. So it is possible to first learn the HLS programming and then take something that exists and redesign it. So that can also be done by these the AI-based reverbs and things like that as well.
Okay.
But GPUs are still probably a better option for AI-based stuff than FPGA.
And if I want to get started with FPGAs, if I just, let's say, get an FPGA, can I just download the HLS file and run it on the FPGA? Is that how easy it is?
No, it's definitely not. Unfortunately, it's even just installing all the tools is it's a long process as well. I would say look at the Cifala GitHub because they really have put the documentation well. And doing it from Faust is a good way to get into it, I feel.
Okay. Thank you so much.
Yeah, thank you.
So can I ask, this is basically like for the musicians here, this is like building like a very fancy VCV rack that runs on a very fancy Arduino.
Yeah, you can. That's a big extension, but you can say that something like that. Yeah, the structure is basically what you said. Yeah,
got it. Thanks.
So, how does this compare to DSPs? Like, what are like the biggest advantages that you think that FPGAs have? Because DSPs are very audio specific.
Yeah.
And we are doing audio specific stuff here. So what is your take on that?
Yeah, so I mean the main thing is you can change it. DSPs are fixed, application specific. True. FPGAs you can change it. That's mainly in the end you're trying to make your custom DSP with FPGA. So that's That's the most prominent thing I would say.
Like, would you? So the customizability is the appealing factor here.
With respect to DSPs, I would say so. Yes.
I see. Okay.
Hi. So once I've prototyped some modular synth on the FPGA, can I transfer it to some custom chip? And for example, if because making it on an FPGA is more like a prototyping act, is there a process to go from the FPGA to like a custom ASIC or something?
Yeah, I mean, definitely you can prototype and then you can convert it to a ASIC for sure. And that's also a goal of this because it's easier prototyping and you can test many different options as well. So I'm not completely sure about how to go there, but the goal is like that. This is the workflow that is like what you're saying, to prototype and then fix it. If you're thinking about like large scale production and stuff, that would be the way to go for sure.
Thank you.